cover this session right before we dismiss from class, right? Stable and asymptotically stable. So stable means given that the initial condition is near the equilibrium point, then for any time t greater than 0, it never leaves this equilibrium point too far away. Okay, the distance is always bounded. And for the unstable case, it means that no matter where you started, this one is not bounded. And for asymptotically stable, it means that given the same initial condition, eventually as t goes to infinity, the solution will converge to this equilibrium point. Here is equal to 0, but for stable, the condition is bounded. And assume here is your equilibrium point, and you start from here, x0, and after you start from here, the motion of the states is driven by fx. Okay, driven by this fx. Given the fx, you can draw the vector field or the phase portrait that give you the idea of where it's trying to go. And for a stable case, you can go anywhere around the equilibrium point, but not necessarily converge to the equilibrium point. That's for a stable case. For unstable, start from here, you can go anywhere and diverge, right? And here is not bounded. The distance between this state, which is xt, to the equilibrium point is not bounded. Okay. And for asymptotically stable, which I just write as, implies given any initial conditions x0, and you will eventually converge to the xe, which is the equilibrium point, because it's 0. Okay. And all this motion is determined by these dynamics. Now we're going to head to the next section, which is the preliminary for the Lyapunov function. Here we define what is positive definite function, what is positive semi-definite functions. For the positive definite function, it implies any function which is a value function, not scalar function. 公数有教过啊。Scalar function 就是这个 function 是 scalar。Which is scalar. For vector function, say this is a vector. Okay, this is a 2x2 vector. 2×1的 column. Okay, sorry. X1 transpose X1. Which is a scalar, right? And again, x1, x2 are column vectors of dimension 2. And if you write x1 plus x2, which is a vector, right, of dimension 2, that is a vector function. This is scalar function. A function that is a scalar, a function that is a vector, okay? And for the Lyapunov function is a value function. So a function v here, I mean, it's a scalar function. And it's called positive definite if, here are the conditions. If v0 is equal to 0. When its argument is 0, it's 0. And for the arguments is not 0, v is greater than 0. So which one example is this, right? The value is 0 when the argument is 0. So when the argument is 0, the value is 0, right? When it's not 0, anywhere not 0 is greater than 0. What is positive semi-definite? Means 0 at 0, a simpler case. In this case, is it 0 at 0? It's a 3D case, right? X represent x1, x2 column. So is it 0 means 0, 0 at this point? Is the v function is 0? 是吗？是吧，对不对？ What's this function looks like? So this is PD, this is PSD. So this function is similar to this. Okay, so it's 0 at 0, right? 0, this is x1, x2, and z direction is the v function. So at the origin is 0, 0. Any other location that could be 0 for v value? Yes, on this axis and this axis, right? Whenever your x2 equal to x1, this v will be 0. x1 could be 1, x2 will be 2, so it's not 0. Why is semi-definite? Because when it's 0, the only location or the only potential argument will have to be 0. Only at one location, which is 0. So in this case, more than the origins have contained the argument that result the v to be 0. Then it's PSD. But for PD case, only one point or only one argument that can lead to a 0 value of v. Okay, in this case, it's positive definite. And these functions are very useful to define the Lyapunov function, and they are properties to investigate the stability conclusions. And again, you have positive definite, and of course you have negative definite, and the definitions are the same. It's 0 at 0 and negative when it's non-zero. Okay, so for ND, it looks like this. Okay, with minus, you just add one more minus. Okay, here is x squared minus x squared. And these functions could also be PD, right? And if you add minus in front of this x1 plus x2, it will be negative definite. And for negative semi-definite, condition is could be 0 for x is not equal to 0. Not only one argument that can lead to a 0 value of v. Based on top of the previous section, in these slides, what I want to say is, given this PD function, positive definite function, okay, agree, right? Only at the origin, the value, v value will be 0. And now, given some v value, say v is equal to 3, v is equal to 1 or 1, 2, 3, okay? What are the contour of the x1 and x2? It's called level surface. Let me just say level surface. So these three, here is a circle because of this function. It's symmetry. So it's 3 circles with different radius. Okay, so it's kind of like it takes a slice on different heights of this function. You get these 3 different contours, right? So what does this mean? This means that, okay, if I define some v function, for 3 cases. One is v x1, one is v equal to 1. then given this condition, what are the x1, x2? It's any x1 and x2 satisfy this condition, right? And there will be a circle, right? This circle. So for any x1, x2 that you can say all these, so there are infinite number of solutions of x1 and x2 satisfy this condition, right? So that means there's a set. For in this set where x1 is belong to a real number, x2 belong to a real number, let's satisfy this condition. Okay. So this set is defined as for any x1, x2, real number x1, x2 satisfy this condition. Then I call it label set. Okay. Label set. Okay. And in this case, the label set is this circle with radius of 1. Here is another label set. So I call x1, x2, x3. Now there's a question for Vx, x1, x2. Did you agree that for some y1, y2 belong to S1. This second slide, which is also a PD function, right, is also positive definite, which is 0 at 0. V is non-zero for other way, right? But the label set is not circle anymore. Given some label set condition, let me write down. Okay, Vx and again V when any, let's define a label set for list to be 1. I say there's a label set S1, okay, Vx1, x2, which equal to 2. There's a label set, say 2. Definition is the same. Okay, so these are labels at S1, S2. Different condition is this is equal to 1, equal to 2. The height of V is equal at 1, equal at 2. Okay, the question is brainstorming. Okay, if I give you some x2, x3, x4 belong to S1, okay, y1, y2, z1, z2 belong to S2 set. Okay, y1, y2 is in this orbit. Okay, z1, z2 is any point in this orbit, in this set. Question is it or x1, s2 is s1 plus greater than y1 square. Is this true? 这个就等于 z 的 norm 嘛 ，this is equal to y norm。 y and z are some states, okay, like x1, x2 is equal to x is defined as a vector which is composed of x1 and x2, okay? So it's condensed to one variable, okay? So it's a vector function, okay? And y1, y2, z1, z2 can be condensed to be y and z. Okay? My question is this greater than this, given that z1, z2 is in level set of S2 bar, and this is in S1 bar. Is that true or not? 就是说，你有任意一点在这个 level surface， 跟任意一点在这个 level surface S1 叫跟 S2， 是不是点上任何一点，它到 origin 的距离一定会大于这个 orbit 上任何一点到原点的距离，会不会 ？So this kind of the distance to the origin, right? Given that y is in level set of S1, z is in level set of S2. You can consider it a satellite travel at this orbit, a different satellite travel at this orbit. Is the distance to, say, Earth, is the distance of this satellite to Earth is always greater than the satellite to the Earth. Is that true or not? In this set, v value is greater than this set. Sorry, too many arguments. Let's be consistent, y1, y2, z1, z2. Otherwise, you'll be confused. Okay, it's clear. Level set 1 and 2, v value are different. This v value is greater than this. Okay. But this is not always true. Okay. Because what you know, they can guarantee is v value for all argument in this set is greater than the set of this v value, right? But that's v value. V value defined as this, the coefficient here is 4. But this is the norm of the argument. There's no 4 here. That's why the contour of level set is ellipse, right? But the distance from the point on any orbit to the origin is not always greater than the point on a smaller orbit. Okay? 给你一个反例，这叫 S1. This is S2. Okay? Greater value of V, smaller value of V, and that argument y, z, right? Y is any point on the orbit. If I choose y is any location on this orbit, right? So if I choose y to be here, y, z to be here, and the distance of y is this to origin, right? And the distance of z is this. Which one is larger? Right? But what's the v value if you evaluate at this point? What's the v value of this? What's Vy? Vy is any point in this set which is equal to 1, right? Because S1. But v value of z is 2, right? So v value, this one smaller, y is smaller. Okay? Remember from the first case I mentioned that you don't know the solution of a nonlinear dynamic system, right? You have no way where the state, where the point will be for any time, right? You had a vector field, you know the dynamics, you know the momentum of this x is. That means you know where it's trying to go, but you cannot guarantee the location of x for all time, right? So, but what you will know in the next few minutes is the v value. Okay, I know the v value, but I don't know what is x. And you cannot conclude that a greater v value means the larger the norm or the argument. Again, it is preliminary. Okay, and we will talk about stability then in a few minutes. It will be more clear to you, okay, what this is about. So for any, consider any quadratic function. Any quadratic means of this structure, okay? C1, C2 are some constant coefficients. It could be 1, 1. We just mentioned 1, 1, right? And 1, 1, 4, which is here, 1, 1, 4, okay? And all these type of quadratic function will be positive definite because it's 0 at 0. Okay. So if z is PD, this function is PD, when at 0 and is x1, x2 will be 0, yes or no? 是吗？我们现在都要从 z value 去反推 x. Okay. We now want to investigate given z value, what is x1 and x2. So given z is 0, is x1 and x2 will be 0. True or not? Only solution, 0 at 0, so it's true. If given a level set, which z value is c, what are x1 and x2? It will be on the level set, right? And x1 and x2 could be anywhere on the orbit because their z value is the same as c. Okay, it's not at a location, it's at a set. Next. This is the question I just showed you, that given an x and y on different level set, if x level value will be greater than y, the term implies its distance to origin is greater than y. Okay? Another key point is if you find after a delta x and a delta y, after the state change from x1 to x1 plus delta x. How do you know, given the dynamics, how did you know the change of z value? I know the dynamics, right? That means I know the momentum of x. Can I use this condition to see what the x plus z minus z? Can I know the differentiation of delta z? If I know what the momentum of the argument, can I know what's the value of z? It's possible, right? We don't know this solution, but if we can know the change of z, and it says z will change to 0, that means the argument reached to the origin. And in this case, you don't need to solve for a solution and it guarantees the stability, which is asymptotical stability. We don't need to solve for a solution, but given this ODE, we don't need to solve the solution, but use this ODE, if we can infer what's the change value of z, and if you are lucky that z will decrease to 0, then you can conclude that at 0, that argument will also be 0, right? And it's asymptotically stable. And that's the spirit of the above function, which will be discussed later. So for question 4, this is my intention to bridge the gap between what you learn and what is the above function. So how do you evaluate this? Can you do this? You can do this by using chain rules. If at t1 is at t0 is here, and after some t1 is here, t1, the v value which is on the z direction is changed with time, right? It decreases with time. Eventually, v will reach to 0, right? At 0, the only argument, the only possibility for the locational argument is at the origin. So how did you prove? How did you find delta v with time? You can use chain rule. So instead of find this, we find the time derivative of v, okay, which is defined as dt dv, right? Anyone in the world know this? Use chain rule. What will you put in here? X, right? You have no choice, X. So what is this? The dynamics, right? Dynamics. V. Once you define the V, this automatically pop out, right? For example, if your V is x1 squared, it's just gradient. Gradient is a gradient defined as partial V partial is equal to partial V partial x. Okay， 因为 v 的 argument v 是 x 的函数嘛，所以你 gradient 一定是对 x 做 gradient， 不会有 t。So what's this? It's 2x. Again, because you have two arguments, right? Okay, so there will be a column vector. So what's this? V is this. Partial with respect to x1, that's 2x1. It's 2x2. So it's known, okay, and this is known. So this, the trend, the time derivative of v is known, okay. And if the time derivative is negative, if this is PD, okay, positive definite, which says is 0 only at 0, and if V is negative definite for x not equal to 0, okay, if x is not equal to 0, that means anywhere other than 0, which is here and here, it's always decrease. Then you can say, given these two conditions, given 1 and 2, v will reach to 0 as t goes to 0. 对不对? Right. If v is 0 and v is PD, this condition guarantees v converge to 0. Your x converge to 0, right? So it's asymptotically stable. Okay, 能懂吗? So again, did you solve the solution of ODE? No. We substitute to this chain rule and evaluate this value is positive or negative. So in this process, you did not solve any ODE. Okay, so this is the way we evaluate the differentiation of z with time. This is Lyapunov functions, Lyapunov series. Okay, so it says given x equal to 0, be an equivalent point. So the Lyapunov function says given x 0, which is a equivalent point. Okay. At x equal to 0 is an equivalent point for an autonomous system. Autonomous system, which we defined before, that is this f doesn't explicitly depend on time, only depend on states. Okay. Define x equal to fx. Otherwise, and for non-autonomous system is fx and t, okay, explicitly depend on time. Here we consider that for autonomous systems. So their phase posture is stationary. D is a set belong to Rn, be the domain containing a real region. Say this is D. N dimension. In this case, it's 2D, right? X1, X2, so it's 2D. And this domain D contains the origin Xe. Then let a function V mapping from D to R. So mapping means you map an argument to the value of the function, right? Some kind of like fx. You map x to fx, right? Okay, like a machine, like a vendor machine, 投影机. You put your coin, right? Put your coin inside. Coin is your x. Fx is your beverage, 你的饮料，对不对? So this is your input, and you will get some value, which is called fx, okay, or y, sometimes usually. But this is the domain of your argument or your input. This is the domain of your output. For the overall function, it's a value function, so this one had to be one dimension. Okay, but input could be R1, R2 to Rn in general, depend on what the dimension x is. In this case, it's D, right? Because D is your state. This domain is for the states D, so it's mapping from D to some value function. So V had to be continually differentiable function. Otherwise, remember, it had to be continually differentiable, C1. Otherwise, the solution is not unique. But if it only satisfies C0, the solution only exists, but not unique. Okay. So the initial condition for V is V0 at 0, and V is greater than 0. This is PD, the requirement for a PD function. Anywhere in this domain that and exclude this, the value of Vx has to be greater than 0. It's kind of like this. Okay. And in this case, if you can find this V and you know the derivative of V is negative, means V value always decrease. Okay. Then your x at 0 is stable. Because V dot is negative, that includes D. And remember, D contains x0, right? But in the second condition, D subtract 0, D excludes 0. Okay, Dx should be less than or equal to 0. And this condition is called PNSD. Okay, so maybe let's go back to a few slides for the definition of SD, which here, right? Less than or equal. Okay, less than or equal. Okay, so that means given a PD function and your V dot could be equal to 0 when it's not at the origin, say here, maybe at here, okay, at here, which is not at the origin, and V dot at this point is 0, means it stopped decreasing, right? It keep at this level set, and in this level set, we know the argument is not trying going to the origin. It stopped here in this orbit, which is not 0. So it's only stable. It doesn't go anywhere. It doesn't go outside of this orbit. Just keep staying on this orbit, right? Because V dot is 0. V is constant, right? V is constant means it's a level set, right? Level set means the set containing all the states or all the argument. Level set 不是切个 slice 吗? And all the argument on the orbit is a level set, and which means when V dot equal to 0, V is constant. V constant means V is some value. Okay, so the x is in the level set. 那这时候 v 就不变啊 ，v 不变表示说这时候我的 x 我用 v 去反推 x 嘛，这时候所有的 x 都满足这个 v value， 那也就是所有的 x 都待在这个 orbit。Okay, so it's called stable. But if you can find the condition that it always decreasing outside the origin, okay, always decreasing any point outside this origin, v is always decreased. Eventually, v will reach to 0. Basically, this function is a virtual function, right? This default function doesn't exist. What is physically exist is the dynamics of a car or a mechanical system. This exists, 对不对？对吧？这是存在的，这是你用来 model 一个 dynamics, 一个 physical system, right? And based on this, you can plot the phase portrait. 对不对？你可以 plot 一个 phase portrait， 对不对 ？You can plot a phase portrait. So assume this is 0, 0, and you start anywhere from here. Initial condition is here. And use this phase portrait, you can plot the trajectory. You can plot the trajectory of the state. Again, we have no idea what the solution to this ODE is. We don't know what this trajectory is. Therefore, we define a default function in the z direction. Okay. And each point on the x1, x2 plane have a mapping, right? If you define this function, you can choose the function. For example, this x1 squared, x2 squared, or whatever is positive definite, right? But in this example, for x1 squared, x2 squared, it's this kind of shape. So everything in yellow is virtual. And why you utilize this function is, given any point here, okay, here, given any point here, that, and according to this vector field, there is this vector describes the motion of this state at this location. If you project or substitute this function, you will get a v value, which is of this z-axis. Our objective or our hope is trying to see if v value will decrease along the trajectory. Because we know if you keep decreasing along the trajectory, eventually v will reach to 0. So does the states. 刚讲说 v dot equal to vx times the dynamics, right? And we want to evaluate if this is negative. Because when it's negative, okay, if it's negative, that means this value keep decreasing. And this value, maybe at t1, x is here, and using this corresponding vector field, t2 is here. And t1, t2, these states have a different v value, maybe here, right? They have different value. And you compare the two. If this is smaller than the previous one, we say a v dot maybe is negative, right? And if that's also the case, eventually it will reach the 0, right? And based on this function, the 0 value of v means x1, x2 are 0, which converge to the origin. No matter where you are, if v is 0, that means this trajectory converge to the origin. And this means a syntactical stability. So we don't need to solve the solution, we just evaluate this. So all the property is condensed to this property, okay? 那我目的是要让不管它在哪一个 x， 它 v 都是往下的，也就是 v 都是小于0的。所以我想要 v 小于0，不管它在哪里嘛，除了原点以外的地方，我 v 不管在哪个点，我要找到的 v dot 它是小于0的，表示说不管在哪里，它都会偏吸到原点。The reason you put equal sign here is it's stable. stable means it doesn't converge to 0, but it doesn't go anywhere， 对不对？你看一下 label set 这个嘛，你投影到 z plane， 我们讲过，这个是 z 方向是不存在的。You need to project to this x1, x2 plane, right? Because it physically exists, but not in the z direction. Z is only for your reference. If v dot is 0, in some d in here, okay, if v dot is 0 here, that means that v is constant. When v is constant, x1, x2 could be any value satisfy, for example, 1, right? 这时候你的 x1, x2 有很多 value 嘛，就是任何 value 在这个 orbit， 它的 value v value 是等于1的时候嘛，对不对？这些点都符合嘛？那这些点是等于0吗？不是嘛，它是在 D 里面嘛。OK， 那这时候不就是 stable 啊？因为它不到平衡点嘛，它在这里。It's not converge to 0. It stay away from 0, but it doesn't go anywhere, so it's stable. The equal sign here, but here there is no equal sign. It was forced to be negative. The only chance is you had to decrease no matter where you are, other than 0. If it's 0, means anywhere in D. That means no matter where you start here, and it just stay here. It doesn't go anywhere. There's no dynamics. The dynamics can be if v dot is 0 in D. In D means v dot 0 means v is constant. V is constant. X is in the level set. So depend on what your initial location is. Okay, the level set is any orbit with v value at here. Okay, v value at here. 听懂吗？所以你一放上去，它就开始存在这里面，在哪里我不知道。I don't know the solution of x, but what I know is in this orbit because v value is constant. 听懂吗？ So it have to decrease, but it stop decrease somewhere before it reach to 0. That is stable. 懂吗？它没有走到 0 之前，也就是它在半途 D 的时候 ，D 就是 include 还没有到 0 嘛，它就可能等于0了。V dot is equal to 0 means V become a constant. 懂吗？这时候它就是 stable， 因为它就是在这边嘛，它不会去 origin， 它也不会 go away， 所以它就是 stable. So I just mentioned here, right? Use the chain rule. So in general, there's a term called the derivative. So given a dynamic system, okay, it's kind of like f equal to some ODE. And if you choose a level function, which is PD, then its time derivative v dot is equal to this. Okay, use chain rule. So on the right hand side, the x dot here is the dynamics, so you can substitute minus x, right? Substitute your x dot is here, so you substitute minus x. And the gradient of v is x, right? You take the gradient, is x. So what you get is minus x squared. What does that mean? Minus x squared means anywhere if x is not 0, this guy decrease. This guy is negative, and this guy have to decrease. The dynamics of x dot equal minus x. Assuming you don't know the solution, okay? But in fact, you can solve for this linear ODE. But assuming you don't know the solution, so evaluate at this point x equal to 1. We know x dot is minus 1, which means it's trying to go back to the origin. Evaluate v value here. What's the v value here? When x equal to 1, you substitute to the default function. That would be 1 over 2, 对不对？对吧？那你觉得呢？你觉得 if you use these dynamics, what would be v dot? 看图就知道，对不对？ Because you're trying to move back. So if you move to next time, if it's here, v value will be smaller, maybe 1.25, 0.25. So based on this figure, you know it's negative. But if you use numerical measure, it tells you at x equal to 1, the v dot is -1. And this fact matches this observation, right? 对不对？两个是符合的嘛，没错嘛。它一定会往这边 move 嘛。Based on this dynamics, right? You substitute one here. The x dot is -1. X dot is motion, and it's trying to go back to the left, -1, right? 所以当它移到这里的时候，它投影的这个 v 值一定会往下嘛，因为它投影到这个线上嘛。这个点投影到这个线上会到哪里？这里嘛 ，right？ 它这个值不是比原来的还要小吗？对啊，所以随着时间变化，它的 v 值会下降嘛，也就是 v 大是 negative， 懂吗？懂吗？啊，什么时候会等于0？什么时候会等于0？就对不对？所以我们上一页才把那个 zero exclude 掉，这样懂吗？ So the reason we exclude 0 here is because in this case, at the origin, okay, the gradient of this function is 0. The slope is 0. So that means your v dot will be 0. That's why we exclude 0. Okay, 看到吗？最小值嘛，一个 function 的最小值，它的 gradient， 它的 slope 不是 0 吗？对不对？它的 slope 是 0， 它 v dot 一定是 0 嘛。Okay, so basically, this part, this v function doesn't exist physically, right? It just help you analyze the stability. Okay, so this is a gradient. The second part is associated with the physical dynamics. So what is the gradient of this function at this point? If you use visualization, it's this slope, right? 对不对？ gradient 啊 ，gradient 不是斜率吗？这个 function 对 x 的斜率啊，对吧 ？So what's this? Gradient of this is x, and substitute x equal to 1, which will be 1. Okay, the slope is 1. It's 1. It's positive. If this is positive, okay, move to the right means it's positive. This guy will increase, right? Because it moved to the right. Based on the slope, you will reach to this value. So v will increase, 对吧? The physical meaning of this v dot. The motion of a state, the configuration or the slope of this configuration, 对吧? 对吧? So if you move to the left, which point to the negative direction, v dot will decrease, okay? Because you will reach to here, and the corresponding v value is decrease. 看到吗? In this figure, this is phase portrait. Okay, this is the gradient of v function. This is the dynamics. X delta t. When you multiply two vectors together, it's a dot product, right? 内积，你把两个向量做内积，你把两个 if you make a dot product and you prefer this guy to be 0, right? Means the two had to be in the opposite direction, 对不对? Right? So, given such kind of function, the gradient is point outwards. And if you want your v to decrease, the dynamics, the vector of this dynamics have to be in the opposite direction of your gradient. Means your x had to point inwards. So what does that mean? Your dynamics had to point inwards. In this configuration, for x dot point inward means it's trying to reach the origin. And in this case, your gradient and your dynamics are in a different direction. And which case v dot is decreasing. So this configuration is very virtual. What really exists is this trajectory. This is the dynamics of a physical system. But you create a virtual function which gradient is point outwards. And you can say, because I don't want to solve I cannot solve the solution, but I can know from its dynamics that if this dynamics which associate with the vector field, or the momentum that state trying to move. If this direction is point in a different direction of my gradient, I'm safe. I will eventually converge to the origin. Okay, another example. So given a dynamics and autonomous system, x1, x2 in a 2D space, 你有一个 x1 dot x2 dot described by these ODEs. Okay, is this system stable? This is usually an engineering question, right? You have model a mechanical system that give you this kind of dynamics, and the question to ask is this what is the equilibrium point? Is this system stable or asymptotically stable or unstable? It might be hard to solve this solution, but Lyapunov function or Lyapunov theory could be the tool to evaluate stability for this kind of system. Okay, we don't know the solution of this system, but we have the dynamics, and you can apply to the Lyapunov theories. Okay, so what you will do is first evaluate equilibrium point. So, and in this case, equilibrium point is 0, 0 because you let this equation to be 0, that this equation to be 0, you can solve for the solution of x1, x2, which is 0, 0. Define, you have to find a Lyapunov function. If this Lyapunov function doesn't fit, try another Lyapunov function. There is no systematical way to find the Lyapunov function. But if it's a linear system, then you are lucky. You can use LMI, which stands for linear matrix inequality. To find the Lyapunov function. Okay, but for nonlinear system, usually it's hard to find. Inequality. Okay. So we can search for this keyword. Okay, if are even interested. But here we just randomly pick up or design a Lyapunov function. Okay, and try what's the v dot. So the first step is you had a gradient of v. So this is PD, right? Positive definite. Okay, and x dot. So what is gradient of v? Gradient of v is right. What is Vx? Is that dynamics? Right. After you tell a gradient, this will be a row vector, not column vector. So your v dot will be x1, x2 times this guy. Okay. There will be x1, x2 minus x1 squared. Okay, plus the second part, x2, x1, x2 minus x2 squared, x1 squared. Okay, let me put minus here. V is PD, V dot is ND, that is AS. You don't need to solve the solution. You know x1, x2 will go to the origin in time as t go to infinity. Okay, no matter where you started. If you don't believe, what you can do is x1, x2 and plot out. Maybe you plot here, choose any initial condition, okay? and see what's the vector field according to the dynamics. Okay. Based on these two, you can construct the vector field, and you point out you vary at every point. Eventually, they will converge to the origin. And what we do here is we construct this Lyapunov function, which is again like a ball. Okay. And we know that given these dynamics, okay, the projection v values is always decreasing along the dynamics. Okay, it's keep decreasing because veta is negative, definitely. No matter where you are, right? You substitute at this location and this location, you substitute. It's always positive and always negative, right? So veta is always decrease. And based on this configuration is positive, definitely. The only chance for zero Lyapunov function is at the origin. Okay, so a question for you. This is PD, right? But if you choose a Lyapunov function that is PSD, 这个也是 PD 嘛？它只有在零的时候才是零嘛，其他地方不是零。Okay, so this is also PD. It's only 0 at 0. But if you choose this kind of Lyapunov function, you will be in trouble, right? Because how many minima do you have? You have C1, 2, 3 local minimas. What happened at this local minima is this is equal to 0 at this local minima, because this stands for the slope, right? And the minima, the slope is 0. So if you are not, if possible, you don't want to choose this kind of Lyapunov function. Okay, even it's PD, but it's not a good Lyapunov function. Okay.